So here's a problem, so number 18, so simply calculating the frequency of light of a certain wavelength. So this is going to be C equals the wavelength times the frequency. In this case, you're given the wavelength. So the speed of light, 3.0 times 10 to the 8th meters per second equals, in this case, 486.1, and that's nanometers, so I'm going to convert that to meters, 10 to the minus 9th of a meter times the frequency. So obviously what I need to do is divide both sides by 486.1 times 10 to the minus 9th meters. Meters is going to cancel, leave me with per seconds. This cancels this side, and I'm solving for the frequency then. And that is problem 18. Now in problem 19, so we have this pulse of light that comes out, and it is 525 nanometers, and it has 189 times 10 to the third, so it's kilojoules, joules of energy in it. And using these E equals H nu, that is per photon. This is joules, and it's in joules. It's a bigger number than what you're ever going to get with a single photon, and that's what this is about. How many photons are contained in this pulse with this much energy? So there's a couple ways you can do this problem, but the way I'm going to walk you through here is that we'll calculate the amount of energy that's in, so H nu, that's in per photon. We're given the wavelength, so we're going to do this as H times C over lambda. For joule seconds, that's H, times 3.0 times 10 to the 8th meters per second, and that's all over, in this case, 525 times 10 to the minus 9th meters, so we can cancel meters, we can cancel seconds, and that tells us how many joules there are in one photon then. That is per photon. So let's do that. And that answer, what I end up getting then is that turns out to be, so this is 3.79 times 10 to the minus 19th joules per photon. So we take that, we're going to have photons is what we want, and that is 3.79 times 10 to the minus 19 joules, and I multiply that by how many joules this is 189 times 10 to the third joules. Joules is going to cancel, and it tells us the number of photons that we get in that pulse. Okay, in number 20, this is then a photoelectron effect problem. So we've got our metal with our atoms in here. And the question is, light comes in, H nu, and this threshold is 1.76 times 10 to the third joules per mole. And we want to know what is the wavelength of the photon needed to equal that. So it's going to be, this is in joules per mole, so we're going to have to get rid of that mole again. So this is what we're going to do first, is get rid of that mole. So it's going to be 1.76, so 1.76 times 10 to the third joules per mole times 1 mole over 6.082, 6.022 times 10 to the 23rd photons. And that's going to end up being joules per photon. And that's going to be the wavelength we need. I realize I made a mistake here. So this is 1.76 times 10 to the third. This is up here, 1.76 times 10 to the third kilojoules. So this has to be 10 to the 6th if I'm going to do this in joules. 10 to the 6th joules, okay? And so what this turns out to be, and I do this, 2.92 times 10 to the minus 18th, so minus joules per photon. And then I can plug that right into h nu E equals h nu, and that's right at the threshold, equals h times c over lambda, and then I can solve for lambda. So lambda equals hc over E, which in this case is going to be Planck's constant, multiplied by c over this E right there that we just calculated. And that'll give one of these answers, and that turns out to be 68.0 is what the answer turns out to be. So you have to keep your units right. And I'm not going to work this out because I'm just running out of space. I'm being real sloppy. I'm running out of voice, all kinds of things. So that's the way to finish that calculation out, and that'll tell you the wavelength that matches that threshold.